Hi students, our topic is revisiting rational numbers and their decimal expansion. What is a rational number? Rational numbers are the numbers which we can express in p by q form where p and q are integers. This means every rational numbers we can express in a fractional form where p and q are integers and the denominator should not be equal to 0. Rational numbers consist of natural numbers, whole numbers, integers, fractions, decimal numbers. Decimal numbers can be classified into terminating decimal numbers and non-terminating recurring decimal numbers. So our topic is decimal expansion of rational numbers now. Let us write with some examples. Decimal numbers terminating means the number gets terminated after some decimal points like this. Okay, non-terminating means the number it's not getting terminated after the decimal points and it will start a particular pattern after some decimal point like this. Number 3, it's repeats, and this decimal expansion it's not terminating anywhere. And other example I can write like this. Okay. And how to identify the decimal expansion of a given rational number is terminating or non-terminating without performing the division. This means for a given fraction, okay, how we will identify the decimal expansion of that fraction is terminating or non-terminating. That we are going to discuss now. For an example, I am writing 3 by 8. It's a fraction. It's a rational number. How I will identify if I am expanding this fraction as a decimal, that decimal number can be terminating or non-terminating, right? So how I will identify this? Normally, we will do the method of division to identify this. Okay. By the division, we got 0.375 as the decimal expansion of this number. It's a terminating number. But our topic is how without performing the division, how we could identify this as a terminating decimal expansion. That we are going to discuss now. First I am writing the example of yes 2 by 10. Okay, 2 by 10 is we know 0.2. 35 by 100. 35 by 100 again I can write as the power of 10. 100 is 10 square. It's 0.35. 375 by 1000. Okay, this is 375 by 10 cube. This means 0.375. Again I am writing 8225 divided by 10,000. This one again I am rewriting it as power of 10. 0.8225. Okay, so what we can conclude? These all decimal numbers are terminating decimal numbers. See, it's not repeating, right? It is terminating after some decimal points. So if the denominator is a multiple of 10, okay, it's 10 or it's a power of 10 or a multiple of 10, we can say that the number, the given fraction has terminating decimal expansion. Okay, and in other way we can explain this. 10 is a factor of 2 and 5, right? 10 has the prime factors 2 and 5. Okay, so again we could rewrite it as 2 by 2 into 5, right? Here 35 divided by, for 10 I am substituting 2 into 5, right? Then 375 divided by 2 into 5 cube. 8225 divided by 2 into 5 raised to 4. Instead of 10, I substituted 2 into 5. Okay. So again 2 divided by 2 into 5. Here 35 divided by 2 square, 5 square. Here 375 divided by 2 cube, 5 cube. Here 8225 divided by 2 raised to 4, 5 raised to 4. Okay. So again we can conclude if the denominator is the power of 2 and 5, we can say that the decimal expansion of a given fraction is terminating. Then the next case, if the denominator is not in the form of power of, this is generally we can write as 2 raised to n, 5 raised to m. Okay. So if the denominator is not in the form of 2 raised to n, 5 raised to m, the decimal expansion of the given fraction is non-terminating. So in this way we are checking the given number is terminating or non-terminating. These results we can write formally as some theorems. Theorem 1.5. Let x be a rational number whose decimal expansion terminates, then x can be expressed in the form p by q, where p and q are coprimes, and the prime factorization of q is of the form 2 raised to n, 5 raised to m, where n, m are non-negative integers. If you have any doubt about the numbers coprimes, let us discuss that first. Coprime numbers is a set of numbers which don't have common factors other than 1. So in these theorems, we always take the denominator and nominator as coprime numbers. Like example, I will write here 23 by 100. Okay, there is no common factor other than 1. Like 3 by 8. Okay, or 5 by 11, or or 23 by 15. Okay, so these all numbers, it doesn't share any common factor other than 1. And see all the set of prime numbers like 2 3, 5 7, 7 11. Okay, all the set of prime numbers will be always co-prime numbers, and the consecutive numbers like 2 3, 4 5, 6 7, 7 8, so on. All the consecutive numbers set also will be co-prime. So we are taking these type of numbers as nominator and denominator. Come back to our theorem. Then let x be a rational number. X be a rational number whose decimal expansion terminates. If x is a rational number, how we can represent that? As a fraction. So I take as an example 23 by 100 here, whose decimal expansion terminates. Decimal expansion will be like this, it terminates. Then x can be expressed in the form p by q, where p and q are coprimes. Here p and q are coprimes, right? And the prime factorization of q is of the form 2 raised to n, 5 raised to m. So here again we can rewrite it as 100 as 10 square. And what are the factors for 10? 2 into 5, the whole square. Okay. Then 23 divided by 2 square, 5 square. Now the denominator q is of the form what? 2 raised to n, 5 raised to m, and n and m are non-negative, positive integers only. Always the power of the denominator will be positive only. Okay, so it satisfied our theorem. Again we can take one more example. I take 3 by 10. Okay, 3 by 10 is 0.3. Okay, so we can rewrite it as 3 by 2 into 5. That means 3 by 2 raised to 1, 5 raised to 1. Again, it is of the form, denominator is of the form 2 raised to n, 5 raised to m. So, if the denominator is of the form 2 raised to n, 5 raised to m, x we can express as a terminating decimal number. Okay. Then come for theorem 1.6. Theorem 1.6 is let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 raised to n 5 raised to m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. This is just a restatement of theorem 1.5 only, but a bit changes there. Let us check that with an example. If I write an example of 3 by 8, okay, check the denominator. 3 and 8 are co-primes, that is okay. And check the denominator part. It is not a power of 10, right? It's not in the form of 2 raised to n, 5 raised to m. What are the prime factors for 8? That's 2 cube. 2 into 2 into 2, 2 cube. We can write like that. Okay, so the only factor is here, it's 2. It's not in the form of 2 raised to n, 5 raised to m. Only 2 raised to n is here. So, how we will conclude this has a decimal expansion terminates or non-terminates? Here actually, if one number of denominator is either a multiple of 2 or either a multiple of 5, we can convert it as a multiple or power of 10. That means 3 by 2 raised to 3. If I multiply with power of 5, always the power we should take as the same power of 2. Okay, 5 raised to 3. Then denominator, if I multiplied with 5 raised to 3 to balance the nominator part also, I should multiply with 5 raised to 3. Okay, then 3 into 5 raised to 3 is 125. 2 raised to 3 is 8. 5 raised to 3 is 125. Okay, then we can write it as 125 into 3 is 375 divided by the denominator is, it became 1000 now. It is a power of 10 now. Okay, so we can conclude it has a terminating decimal expansion. Okay, so what we can conclude, it's not necessary always the denominator should have both 2 raised to n, 5 raised to m. If either of it is present here, we can convert it as a power of 10. Again, I am taking one example of yes, 13 by 125. 13 by 5 cube. 125. How we will do the prime factorization? Like this. Okay, so I can write 13 by 5 cube. Okay, so here 5 power of 5 only it's present, so we should convert it as the power of 10. That means 13 by 5 raised to 3 into 2 raised to 3, always the same power we should take here, and here also to balance the number nominator part also we are multiplying a 2 raised to 3. So 13 into 8 divided by 125 into 8. 13 into 8 is 104. Okay, 125 8 is equal to 1000. The answer is 0.104. It's a terminating decimal number. This is theorem 1.6. Then come for theorem 1.7. Let x is equal to p by q be a rational number such that the prime factorization of q is not of the form 2 raised to n 5 raised to m, where n m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating. Okay. So we are taking a fraction like 1 by 7. Okay. So check the denominator. These are co-primes. This P and Q are here co-primes. And check the denominator. It's not of the form of 2 raised to n or 5 raised to m or 2 raised to n 5 raised to m. Okay. This is 7. 7 is a prime number. We cannot factorize it again. Okay. So this kind of number always the decimal expansion will be non-terminating, and rational number always it will be recurring only, non-terminating and recurring decimal expansion. Okay, again I am taking an example of 3 by 11. Okay, check the denominator. It's not the form of 2 raised to n 5 raised to m, right? Okay, so again it's we can conclude it's non-terminating recurring decimal number. One more example, 1 by 3. Okay, so again 3, it's not equal to 2 raised to n 5 raised to m, so it's non-terminating recurring. Okay, I hope you understood these theorems well. Thank you for watching the video. Please like and share, and don't forget to subscribe the channel to get notification for new videos.